in the flurry of demonstrations at the end of the hour, I showed you some things that I really had only barely discussed. So I just want to go through the last tidbits of microwave ovens before turning to sunlight. Just things that I think are worth making sure you guys know. And actually, I'll reach even a little bit farther back, and just the idea of radio waves. I kept promising to talk about what happens as they travel and spread out, and I never got back to it last time. What's the issue? That when you look at the radio waves transmitted from a radio station, pick your favorite one in town, the waves go out. They typically have a certain polarization, although the polarizations can be complicated. You can mix polarizations in various interesting ways. That's not so important to me at the moment, but what is important is that the waves typically go out they don't travel just like in a cylinder, just heading off forever in that cylinder. They spread. They get wider in various directions. The waves coming off of a vertical AM radio antenna, and I told you why AM radio antennas, that is, antennas used in the AM band, which are very long wavelength waves. Those antennas are, by convention, they're vertical. They're tall vertical masts. Horizontal is unrealistic. So they're vertical masts. The waves go out primarily in the horizontal direction, which is good, because that's where people are. And if you look above the horizontal, the wave is still there. It's just getting weaker. And when you go to vertical, which is directly above the antenna, there's no wave there at all. Of course, there is some waves sent into the ground, which is sad but true. That's life. But as that wave goes out, if you're near the antenna, you're sort of receiving or having passed through you the wave that was going out in a couple of different angles, a variety of angles, because you're close and you subtend a big angle from the station. But as you go farther and farther away, you occupy a smaller and smaller range of angles from that antenna. The point of this then is that you're seeing less and less of the wave as you get farther and farther away. And the wave does get weaker. And it gets weaker in part because it's spreading out horizontally, and in part because it's spreading out vertically. And there, you could think about it in various different ways. But it's the same thing that happens with a flashlight. The flashlight's up close, it's nice and bright. But as you get farther away, it gets dimmer because it's spreading horizontally and vertically. Less and less and less there. So most radio waves weaken with distance from the antenna. Once you get beyond the really, when you're close in, life is complicated. But when you get farther away, they get weaker with distance approximately as 1 over the square of the distance. So if you double the distance, you get only 1/4 as much power reaching you in the wave. And why the squared? Squared is because it spreads horizontally and it spreads vertically. If there were more dimensions, it wouldn't be squared. But it's squared because of our 3-dimensional world and the spreading in 2 dimensions, in 2 of those dimensions. Is that okay? This turns out to be very important to things like, to radio stations that on the East Coast and West Coast share the same frequency. They don't want you seeing both of them at once. Well, the wave gets weaker from the East Coast wave in traveling all over the West Coast gets very weak. Furthermore, it's often blocked by the curvature of the Earth. But anyway, distance weakens the waves. That's the problem set points out. That's very important to cell phones. When you're communicating with the cell phone tower, you only really want to communicate with one of them, the nearest one. Your cell phone is chitter-chattering back and forth with that one nearest cell phone tower. If all the cell phone towers saw all the cell phones, it would be a mess. You'd be sharing the same frequencies and stomping on each other right and left. So they take advantage of the decrease in intensity in the wave with distance. Any questions about any of this stuff? All right. It allows, actually, so the cell phones use very, very weak transmission power in both directions. It's a very gentle little wave. Your cell phone just barely manages to receive it. The tower just barely manages to receive it back. Somebody in another county using that same frequency of wave has essentially no impact then on your local cell phone communication. Their wave is too weak by the time it gets here. All right. I think that's all the story I want to say going back to radio. I do want to go back though to microwaves, and I said, you know, in 3 seconds how the microwave oven cooks food. Almost all of the cooking in food is done by way of the water molecules. It is, it's a non-thermal heating. Let's see, how does that mean? You're not heating the water molecules by exposing them to the flow of heat. You're not putting them in a hot box or exposing them to the thermal radiation from a hot surface or any of that stuff. You're heating by way of the radio waves or the microwaves. They're short wavelength, therefore they're microwaves. And the microwave oven, in contrast to most of the microwave devices you work with, the microwave oven produces a very powerful wave. So your cell phone, whether they can even produce a 1 or 2 watt wave, I'm not sure. It's somewhere in that territory. That's the strongest electromagnetic wave they can produce, carries with it a power of a watt or 2, something like that. The microwave oven's wave can carry with it a power of 500, 1,000 watts, lots of power. And that's not so difficult for the microwave oven to do because it doesn't have to do anything subtle to the wave. All it has to do is just pour it out there. Your cell phone or the Wi-Fi transmitter or whatever, they have to modulate the wave. They have to play with it to convey information on it. You know, AM modulation, FM modulation, combinations of those two, more subtle things even than those. So those use very sophisticated transmission systems to be able to warble the wave in a very effective way. Microwave oven just lets it roar out there. It uses this old technology known as the Magnetron, I mean old as in World War II. It's a very simple, robust device. You can buy them for sort of like a $10 device, maybe not even that much anymore. And they just pour out microwaves at a pretty well-defined frequency. It's not super well-defined because what determines the frequency in the magnetron is actually a bunch of tank circuits. It just has the inductor capacitor pairing. That's its frequency control. And those tank circuits are very simple because they operate at very high frequency. They don't have very many turns in their inductor. They only have half a turn. They don't have a lot of surface area in their capacitors. They only have 2 surfaces staring at each other. They're actually C-shaped pieces of metal. That's all it is. It's not quite an antenna which has been pulled straight. It's a curved, sort of a curved antenna. And they get that thing going. They feed power into it, which it then turns primarily into microwave power, which comes out, is radiated out by a little teeny quarter wave antenna that's in the side of the cooking chamber of the microwave oven, hiding behind usually some sort of, it's not a metal foil, it's an insulating window. So when you go look in a microwave oven next time, stare inside a little bit, you'll see a little window somewhere sitting up there with a cover on it. Hiding in there is the magnetron's antenna, just a little short stubby guy. As far as the cooking is concerned, the microwaves come roaring out of that little transmitting antenna. They go into the box. The box is all metal, including the front screened window. Remember that? It's metal. It happens to have holes in it, but microwaves, like all electromagnetic waves, have difficulty sensing the presence of holes that are much smaller than their wavelength. And since the wavelength of the microwaves in the microwave oven is about like that, these little teeny holes that are the size of a pencil point, the microwaves can't see those. The microwaves encounter that metal surface on the front window with its holes, and there's plenty of time for current to flow around the little hole during one part of the cycle, to flow around the hole and basically compensate for the hole's presence. Hole schmo, it doesn't matter. So you get essentially perfect reflection off that screen. They can't remove it, of course, which would be nice. You could see better, but if they removed it, the microwaves would come out and you would get cooked a little bit too. The sealing of this 6-sided chamber is pretty good. They don't leak much at all. You can buy microwave leak checkers. I have over the years had a couple, including, I think at some point I had a really fancy one. They almost never leaked, which is nice. So they're all inside. And there's an interlock on all the microwave ovens. So as soon as you pull a door open or whatever, it turns off the magnetron, stops the microwaves, which then disappear. They get absorbed eventually. They get absorbed in a millionth of a second or something. They're gone. So it's not a big deal. But if stuff is inside the microwave oven, of course, it's exposed to these very intense electromagnetic waves. And those waves it's at 2.5 gigahertz, again, 2.5 billion cycles per second. So the electric and magnetic fields in these waves are flipping back and forth 2.5 billion times a second. It's a full cycle 2.5 billion times. So actually the electric field reverses twice that many times per second, 5 billion reversals per second. And that will certainly affect free electric charge. Free electric charge will feel a force when it's in an electric field, so it'll move. And that's why metal is interesting, or interesting or dangerous, or some combination of the two. For most foods, they're not metal. Why do they even care about microwaves? Well, if food, I guess, if it conducts electricity well, I mean, salt water or something like that, maybe you'll get a little bit of heating that way. But the principal way in which foods are affected by microwaves is by way of not free charges, but polar molecules. Water being an extreme case. Water remains it's one of the most amazing molecules in nature. It probably is don't pull punches. It's the most amazing molecule in nature for a whole slew of reasons. And one of its features is that it's a highly polar, it's a dinky little molecule with a huge electric dipole, meaning that it has a positively charged end and a negatively charged end. And I went on a little bit on my story of Mickey Mouse's head. The oxygen atom, it's H2O, right? It's an oxygen atom with 2 hydrogens stuck to it. They are not in line. It might seem like, okay, so how do they arrange themselves? They don't arrange in a line. They arrange because of oxygen. If you remember from chemistry probably, oxygen has 2 lone pairs of electrons. It's got all the orbitals and stuff, which we'll eventually come to a little bit in this class. Oxygen has a structure that has 2 pairs of electrons sitting off in 2 points of a tetrahedron. I'll say it, but it doesn't matter. And then it has 2 single electrons that it uses to chemically bond with things like hydrogen. So it binds with 2 hydrogens, but they are not in a line or anything. They're approximately on corners of a tetrahedron, which is a 4-sided solid. It's a pyramid with only 3 with a triangle base. Anyhow, Mickey's ears are sitting up there on sort of 2 of these features of the tetrahedron, and they're bonded by a bond that you hopefully have heard of in chemistry called the covalent bond, the sharing of electrons. The hydrogen and the oxygen share electrons. Each of them, they're sharing a pair. So one of the hydrogens is sharing a pair with oxygen, and the other hydrogen is sharing a pair of electrons with hydrogen, but with oxygen. But oxygen doesn't play fair. It pulls that pair of electrons more toward it than the hydrogen does. So the hydrogen atoms, each of them, effectively have a charge that's less than that's positive. They're no longer electrically neutral. They're somewhat positively charged. And the oxygen, having stolen more than its fair share of electrons being negative, the oxygen ends up with a net negative charge on it, effectively. I mean, it is what it is. So you can really simplify even Mickey's head down to just this is a blob that has a positively charged end that happens to be the hydrogens, and a negatively charged end, which happens to be the oxygens. So that okay with everybody? Are there any other molecules in common occurrence that are like that to that extent? No, I think that's, water is special. There are many molecules have dipoles, but not like this. So when you put those water molecules, putting in a whole passel of them, just as liquid water, you put them in a strong electric field, they will tend to line up. They experience torques if they're not lined up, and they twist in such a way that they do line up. The positive charge is pushed downfield in the direction of the electric field. The negative charge is pushed upfield in the direction opposite the electric field. So the water molecules tend to align with the field. But the field keeps flipping back and forth. So they align, and then lo and behold, the field reverses and they have to reverse. And then they have to reverse back and forth. And if you put a whole lot of objects in a tightly packed arrangement and force them to go back and forth between everybody, if I had all of you guys pile up down here, tightly packed, and say, okay, face the back of the room now, face the front of the room, face the back of the room, pretty soon people have bruised elbows and shoulders, right? So the same thing is happening with water. The water is forced to go back and forth rapidly, and it effectively rubs in the process. There's no resonance involved here. It's not like an antenna, which has a natural resonance and stuff. And there's sort of mythology around that microwave ovens the frequency of the microwave oven is somehow chosen to match some special resonance in the water, and that's not true. What is true, however, is that the frequency of the microwave oven is chosen so that it's able to penetrate into the food pretty well, but not too well. If they made the frequency a lot higher, it turns out that the absorption of the microwaves would be stronger and the microwaves would not get very deep into food. So you would end up cooking the outside surface of, I don't know, pick whatever your favorite thing to microwave is. On the other hand, if they chose a lower frequency, it would penetrate too easily into the food. It would go through the food too many times before finally there was a decent absorption of it. And you run the risk of basically heating the box and damaging the magnetron. You actually want something in there that consumes the microwaves. So don't make them, if they're too low in frequency, they're just not absorbed quickly enough. If they're too high in frequency, they're absorbed too near the surface of the food and you don't get uniform cooking. So about 2.5 gigahertz turns out to be the sweet spot for normal cooking of stuff. If you're going to go cook an elephant all at once, you need a lower frequency. Don't cook elephants anyway. All right, so you're okay with how it's cooking by forcing the water back and forth? This gives you some insight, as I told you about the burrito, what I call the burrito problem, the frozen burrito problem. That since water as ice isn't able to rotate, the water molecules, ice has a tough time absorbing microwaves. And therefore, it's hard to defrost food in a microwave oven. It's really problematic. The way that microwave ovens usually do defrost frozen food is they cook it for a little while and they hope that some patches within the food absorb enough microwaves to thaw. Which is, they're optimistic. It's likely to happen. You get some thawed spots, which will then get quite hot. And then they turn off the magnetron for a while and they just let heat flow the good old-fashioned way from hot to cold. So the heat diffuses through the food a little bit, melts some new stuff, then they hit it again with microwaves for a while, then they turn it off for a while. That's why the defrost cycle on microwaves is quite slow. What it's doing is it's giving it's a little cooking, then let the heat flow. A little cooking, let the heat flow. All right? You try to rush it, you end up with the frozen and astronomically hot patches that are no fun. There are other things that absorb microwaves in food, other things in food that absorb microwaves. So even food that does not have water in it or that has frozen water in it can eventually absorb microwaves to the point where it gets hot. It's always iffy. Some things do a good job, some things don't. And the fact that you cook from the inside out, or you cook from the inside, is responsible for the weird texture of microwave cooked food. I guess there are microwave cookbooks, but I don't think there are very many chefs who think of themselves as artists who cook with microwave ovens. One of the big problems is that as you cook food where a lot of the thermal energy develops in the middle of the food, you get a lot of steam there often, and the steam then flows out of the food from its center through the skin or through the outside surface and makes it soggy. So foods that are heated in a microwave oven often end up having soggy surfaces, nothing crispy. For the crispiness, you want to dry out the outside surface of the food. You want to have high heat there to caramelize things. None of that happens. All right. Metals in a microwave oven. I showed you, of course, that metals are potentially lots of fun, although not, you didn't hear it from me, right? No, don't do it. Don't do this at home. The issue with metals is they do have mobile charges that can move long distances, and the microwaves will shove them those long distances, and you'll get both currents flowing through the metal, and you'll also get charge accumulating on the ends of things where they hit the end of the road. They can't go any farther. So if you put something that is thin, that is not a good conductor of electricity, but is not zero, so like the defroster from one of those old problem sets, it'll get hot because current will be driven through it. The fact that you don't have a full circuit isn't important. You can still push charge to its left and then to its right, or right and its left. I've forgotten to reverse. You can shove the charge back and forth through it. That's still current, still counts, still gets things hot. So if it's a bad conductor of electricity, it will get hot as the current flows through it. So that's one thing. Avoid things that are thin or poor conductors of electricity. And the other thing is to avoid things that are sharp and conductors of electricity, because then the charge will go to the end of the sharp thing and jump off into space as a spark or as a corona discharge or a full-fledged arc discharge, all the things that you don't want to have happen in a microwave oven unless you're prepared for it. So things like twist ties are the worst. Sometimes I burn those up. When you can do it, it's just you got to be careful. It's always a race to see which happens first. The sparks shoot off the ends like a sparkler, or does it get red hot? The handle of a Chinese food takeout container, surely some of you have done that. It's a lovely antenna for microwaves. It gets really hot, and it can start a fire, or it can brand your hand there with a nice thin line. So don't do it. Yeah.
I put green grape in a microwave before, and it sends out sparks. Why does that happen?
Yeah, the green grape. Did you cut it in half and fold it open?
Yeah, so I didn't cut it in half all the way through.
Yeah. These are demonstrations. It's got enough electrical conductivity. When you take a green grape, or you cut it almost in half and separate it into two halves, you now have a little antenna there. It's got enough electrical conductivity that current will flow from half A to half B and back and forth by way of this little bridge in between. And that little bridge gets hot, dries out, burns up, becomes conducting, and you'll get, it's like a bad piece of metal, like a twist tie. It'll get red hot and shoot sparks and all that stuff. Yeah, so even foods that are nominally not conducting, they're not totally non-conducting, you can get currents to flow in them and have fun and exciting things happen. Is that okay? All right. Last thing I want to talk about before leaving microwave ovens is just one detail. The source of the electromagnetic wave is what's called a magnetron, and here's one of my old drawings of it. It has these C-shaped pieces of metal. Those are the tank circuits. There are actually 8 of them in this drawing. Each C-shaped opening is one of them. And the power, so what I'm telling you at this point is stuff that can go right past you, not so important. The power is fed into these tank circuits to get the charge really sloshing hard in them by sending out a beam of electrons from a wire in the center of the magnetron, this ring of C-shaped cavities, towards the tines of those Cs, the ends of the Cs. And it uses a cute trick involving a magnetic field to make the electrons arrive at the time that adds energy, that does work on the sloshing charge. And again, so far everything I've said right now, if it doesn't stick, who cares? The point is that the clever trick that steers the electrons so that they add energy to the charge sloshing in the tines involves a force that I haven't mentioned before. It's called the Lorentz Force. And the Lorentz Force it's a little weird in its directions. Here's the name here, Lorentz with a TZ at the end. It observes that if an electric charge moves in a magnetic field, it experiences a force. So up until now, I've told you that electric charges are pushed on only by electric fields. And You can make an electric field by moving a magnetic field or by changing a magnetic field, but still, it's the electric field that pushes on charge. This Lorentz force breaks that rule. It's actually the magnetic field that pushes on the charge. And why is there this force? Wait a second, it's a magnetic field pushing on a charge? How's that? Here's the reason for it, why it has to be there. Suppose you just have an electric charge just sitting here. Here's an electric charge because I happen to have one. It's just sitting here and a magnet moves by. So this could be electric charge in one of those coils of wire that I had when I waved a magnet near it and current started moving through the coil of wire. Remember that? Lighting light bulbs up. So if you wave a magnet around near this guy, you will create an electric field that will push on this and it will accelerate. So a moving magnet, for example, a magnet moving to your right will shove this guy. In which direction we'll shove it, it's going to be one of the up-down directions, and I have to think hard to get it right. So you move the magnet by this, and this guy feels a force due to an electric field. But what if, instead of moving the magnet by the charge, you move the charge by the magnet? Hold the magnet still and move the charge instead of holding the charge still and move the magnet. This is just a frame of reference issue. It just matters. What really matters is like who's watching. If you all are sitting there and I move the magnet past the charge, fine. But suppose you're all walking with the magnet. You all get up from your seats and now you walk with the magnet. And now from your new perspective, as everything's going by, the charge goes by you instead of you go by the charge. Is that okay? Can you imagine the difference of frame of reference? In that case, if the charge is moving past the magnet, it still better feel a force. It can't be that if based on your frame of reference, that if we move the magnet past the charge, it feels a force, but if we move the charge past the magnet, it doesn't feel a force. That's going to create paradoxes. So it has to feel a force. And so the force it feels is this Lorentz force. It is pushed. So whether the magnet moves past the charge moves past the magnet, the force shows up. It's given different names. Getting all the details right is a challenge. Again, this is one of these things first-year graduate students in physics suffer over long calculations. What the heck happens? And that Lorentz force is actually very important in everyday life. Two examples, one just it's there and one that's important to you all. The auroras, the aurora borealis and aurora australis, the northern lights, southern lights, where do those come from? They come from the fact the Earth's got a magnetic field around it, and there are charged particles coming roaring at us from the sun, electrically charged fragments of atoms. And when those electrically charged fragments of atoms encounter the magnetic field of the Earth, they're pushed by the Lorentz force. And Lorentz force has this interesting property that if the magnetic field is this way and you, the charge, move that way, you're pushed at right angles to both of those two things, magnetic field and is it to the right or the left? I can't remember. But the result is that there's a lot of motion in a circle. It's very easy. A charge that's moving through a uniform magnetic field, it's all, say, vertically pointing upward. The charge will be pushed to its right, 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 to its right. It'll go in a circle. So charges tend to cycle around. This actually is the basis for a machine known as the cyclotron. You get charges going around in a circle because they're in a magnetic field. In the Earth's magnetic field, the charges tend to circle around the Earth's magnetic field. And they travel, they would circle in place if it weren't for the fact they also have they have momentum along the field, so they spiral. And that spiraling motion, which gets tighter and tighter as they get closer to the poles, traps these charged particles, which is good for us. It keeps them from coming here and bothering us down here on the ground, which was just as well. You don't really want to have these fast-moving, high-energy things come and hit you. But they hit gas molecules up there, and they make the gas molecules glow, and that's the origin of the northern and southern lights, is the spiraling of charged particles around the Earth's magnetic field due to the Lorentz force. Is that okay? A more practical, down-to-earth story. Any of you guys who have speaker systems, including most of the ones put on your head, those speaker systems, like what moves there's little surfaces in there that are moving back and forth, creating the sound. What force pushes that surface back and forth? It's going to be the Lorentz force. How do they do that? They have a coil of wire attached to the speaker cone or the speaker surface. And they run current through that coil of wire in the presence of a magnetic field. So all your speaker systems they've got a magnet in there. They create a magnetic field. And they have a current-carrying coil of wire sitting in that field. And when you run current in it, the charges, even though they're inside a coil of wire, they feel the Lorentz force. And they get pushed to the side. And they hit the side of the wire, which won't let them go for chemical reasons. So they drag the whole wire. And the force ends up acting on the whole wire, which in turn acts on the whole speaker cone and makes it move. So speakers are all about the Lorentz force. A magnet, moving charge in the presence of that magnetic field, you get forces in motion and create sound. Is that okay? As an aside, years ago I went on a visit to a place that was teaching how things work, teaching this course, and they had a lab component to it, which was kind of cool. And the day I visited, everybody, just like you, were making speakers. And you can do it. It is not hard. You can make a speaker. It's a coil of wire, some sheets of paper, and some magnets. Ready to go. And it works, and they can sound nearly as good as commercial speakers. So in a couple hours of work, you got your own homemade speakers. All right? That's it for microwave ovens. One last piece of that it was so fun to see these people, these students, you all in effect, go up there to test their speakers after they made them. You try it, you're pretty sure it'll work. The variety, and you know all these people. You're at least maybe one. You've got the variety pack of students. You've got the cocky, sure person who's absolutely convinced it's going to work fine first time. Okay. You've got the person who has never made anything in their life before and can't possibly have made something that works. And just like the smile that comes out when it makes music and it sounds really good, it's kind of, oh my gosh. And all the other variety pack, you know these people. So it was fun. Too bad I don't have it here, but I don't have it here. Okay, sunlight, on other things. Sunlight is just a continuation of the same story, a little different in what? Light is another electromagnetic wave. How is it different from microwaves and from radio waves? Light's just higher frequency, shorter wavelength. It's the same. We're following a continuing path from radio waves, which are low frequency, long wavelength. We went to microwaves, which are medium frequency, shorter wavelength. And now we get to light. It's very high frequency, very short wavelength. And we can keep going. The next up would be X-rays, and the next up after that would be gamma rays. It's all the whole, it's one long swoop. So now we're looking at light. And just an opening question here, which if you look up at the sky, so we're going to watch sunlight. We're going to watch the sunlight come from the surface of the sun into the Earth's atmosphere, down to us, and encounter various things on its way. But suppose you look up during the day. The stars, the stars are out there. Is the light from the distant stars still reaching your eyes? Is it there during the day? Is it okay as a question? How many think yes? How many think no? Okay, the vast majority are going for yes, and that actually is the answer. There have been, why can't you see it? Because it's overwhelmed by light coming from the sky. Ultimately, it's not produced by the sky, it's coming from the sun, but the sky is redirecting it and to some extent modifying the way, what you see, because you see this blue color typically. But it's an overwhelmingly bright glow coming from the sky, originating in the sun, and it just overwhelms the starlight. You can't see it. The starlight's lost in sort of signal-to-noise problems. It's too faint. There have been stories of people at the bottoms of wells and so on. They look up just at the right time and see stars. But I think I think all the evidence is doesn't actually work. So sunlight's too bright. The scattered sunlight is too bright. The word scattered will come up from time to time as we go along here. Scattered just means that it came in going one direction and then it's scattered, it's going a new direction. So when light gets redirected, it's often, the process can be referred to as a scattering process. It's just jargon, but it is what it is. It comes off my tongue too easily. So some observations about sunlight. The sunlight appears whiter than most light. That's what Al was doing here, was playing with these bulbs. We'll see that what you call as white light depends on context. And sunlight makes the sky appear blue. So we'll look at what it is. We'll look at sunlight and compare it to other lights that aren't colored. We'll also look at why the sky is blue and why the sunlight becomes redder at sunrise and sunset. Why the red sun or the orange sun at sunrise or sunset? There are reflections of sunlight off of things, even things that are not metals, like windows reflect sunlight, a flat surface of water reflects sunlight. Why? And there are certainly contexts in which sunlight bends, like camera lenses and cut crystal glasses or gemstones, and why it gets separated into colors. So that sunlight, as we'll see, is a mixture of colors. It's not white. White is not a fundamental color. It's a mixture of what we see as colors. And they can get separated in materials in nice ways. Like, the classic thing is a diamond, a cut diamond, an engagement ring, will take sunlight, which is apparently white, and will shatter it into pieces that have bright colors. And those bright colors are sort of fundamental colors. Okay, so those are all things to discuss. So the first up here is why does sunlight appear white? And it turns, what's the origin of sunlight? Because that's where whiteness comes from. Sunlight is the thermal radiation coming off of a very hot surface, the effective surface of the sun, or the optical surface of the sun, which is called the protosphere, is that right? Photosphere. The photosphere of the sun, the outer surface. The sun itself, you've heard tell way back that it's really hot inside, right? Like 100 million degrees or something deep in the center of the sun. We aren't able to observe that high temperature. What we see instead is the outer surface of the sun. And the surface of the sun is actually black. It's actually jet black. And what does black mean? This is a topic I harangued about in Physics 1050. But a black surface is one that absorbs all light that encounters it. No reflection. Nothing comes back at you. That's what black really is. And a classic black surface is a hole that goes off into a cave, that's sort of never-ending cave. Because light that enters that hole never comes back. So that's the blackest black people know how to make, is a hole that goes into a vast, empty place. So the sun is jet black, meaning that if you go up there with a flashlight and shine a flashlight at the sun, nothing comes back at you from your flashlight. But just because it's black doesn't mean that it doesn't emit light. Black objects do emit light, and in fact, they emit light characteristic of their temperature. The hotter they are, the brighter they glow, and the more towards a certain end, the blue end of the spectrum they emit. So the sun is a black body. It's a black object. If it cooled off, it would just be a jet black ball. If it were ice cold, it's not. It's so hot that although it absorbs all light that hits it, it does glow with its own thermal energy, and that is brilliantly bright, and it covers a swath. The swath that is primarily what we call visible light. Where does this light come from? It comes from the thermal motion of the charged particles in the surface of the sun. So that last outer part of the sun, you think of it, not only is it black, but it's inky black. So it's like, it's opaque. If you took if you could scoop a chunk of sun out and put it in a container, you wouldn't be able to see through it because it's inky black. So there it is, it's really hot, so it's glowing away. And all the charged particles in that outer surface there are jiggling around vigorously because they're so hot. And remember, accelerating charges emit electromagnetic waves. That's what they're doing. They're emitting electromagnetic waves really nicely. And they're glowing then. The choice of the frequencies and wavelengths of the light they emit depend on their temperature. The hotter they are, if they were hotter still, they would be moving faster and jiggling harder and having higher frequency waves coming out. They happen to be in a range where they emit a spectrum that crosses the whole visible spectrum, what we call visible. This is a graph, I guess, of the spectrum of light, of the electromagnetic spectrum, a piece of the electromagnetic spectrum that we see as light. I've labeled the horizontal axis two ways. One is wavelength, that is how far apart the crests of the waves are, in a very small unit, a unit known as a nanometer, a billionth of a meter, teeny tiny. So this part of the spectrum represented over here on the left by 700, that's 700 nanometers. That is a little under a millionth of a meter from crest to crest, pretty close. And as you go here to the right, that wavelength gets even smaller. So those are even shorter wavelength waves. And on the top of the graph, the x-axis, I've labeled it in frequency. If you recall, there's a relationship between frequency and wavelength. The product of the two is the speed of light. So as the wavelength gets shorter, the frequency gets higher. And how high is the frequency? Really, really high frequencies. This is 4, 5, 6, 7, 8, 9 times what? Times 10 to the 14, which is, I guess that's a trillion. So this is 400 trillion, 500 trillion, 600 trillion, 700 trillion cycles per second. That's pretty fast. I can't move a positive charge up and down that fast. So producing light waves is tricky. You can't do that with conventional antennas because you just can't move the charge up and down fast enough. So that's why light, until recently, was mostly the domain of hot surfaces. The only way we really knew how to produce light was, well, that's not quite true. The main way in which we knew how to produce light was to get some surface so hot that all its charged particles jiggled around and launched waves at this frequency. Since then, we know how to do it with other things like electric currents flowing through gases, which we'll do. Gas discharge lamps, as it were. And lasers. These make light waves in a much more sophisticated way. So we'll get to those. But this is the simplest way to make light. You simply heat the bejeebers out of a surface, and it will start to glow with its own thermal radiation. And the longer frequency waves, lower frequency waves, longer wavelength, lower frequency, we see as red light. And as you work your way through the spectrum, by the time you get over here to these short wavelength, high frequency waves, we see them as violet light. More about that soon, but that's the basic idea. The sun emits a lot of these. It also emits light that we cannot see that's beyond red, called the infrared. And this is a significant fraction of the light that reaches us on Earth is in the infrared. The sun also emits light that we can't see that's beyond the violet end of the spectrum, and hence called ultraviolet. And this also, there's a moderate amount of ultraviolet coming from the sun too. It turns out the infrared is going to be associated primarily with just heating. It doesn't cause chemical changes for reasons that will come along soon. Ultraviolet does. Ultraviolet light is more damaging. It has a characteristic that it can break molecules up. It's called ionizing radiation because it can actually damage molecules and tear them into their fragments, including ions. And so exposure to ultraviolet light is typically not so great for you. Infrared light, it gets you warm. And so you can judge for yourself. If it's too hot, leave. But ultraviolet light, you can't judge so well. It's doing chemical damage to you. There's no obvious symptom except sunburn. Not so good. All right, those colors that I've got, the sort of rainbow colors, are the separated pieces of sunlight. Sunlight being a mixture of all of these wavelengths and a particular mixture, and I don't have a plot of the mixture. It peaks in the green, but it's a whole that whole range is covered. When you mix them together in the right proportions, we observe that as white. Our eyes and our physiology. This has to do with us as creatures more than it does with anything with physics. We see it as white light. But if you do things like, let's see, okay, so we've got 3 different colors here. I know it's dazzlingly bright, but this is a mixture of light. It is trying to simulate sunlight, so that the light you're seeing here, which we would call white light, has approximately the right distribution of the different electromagnetic waves coming at you, so that we perceive that as white, sunlight white. Is that okay? This bulb, 3,000. That's en route to being incandescent light bulb hot. This is still, we would call this white. If you didn't see this guy, if I turned him off, right? If I only give you that, you'd say, oh, that's white too. But it's a different white. Your brain compensates for the fact that when you saw both of them at once, that one's clearly different from that one. But this, you'd call it white. It's more the white of incandescent lighting, Edison light bulbs. This guy, this really over here is the Edison light bulb. It literally is the Edison light bulb. That's yet another white. So what's the deal here is our brains and eyes and brains can compensate for the distribution of the electromagnetic waves that's present in the light source. We seem to have we naturally keep redefining what is white for the current context. So if all you've got to look at is the sun, which is that blue color, we define that as white. If all you got to look at is the Edison light bulb, we define that as white. And this is just natural in us. Well, how would you even label these things? And so this is sort of somewhat of a public service announcement notice, both about light bulbs and for cameras and things like that, is when you buy light bulbs these days, and light bulbs, certainly in my lifetime, they've evolved. This was the light bulb of my youth was this, right? And then in middle age, this was the light bulb. And now, in my dotage, it's these light-emitting diodes are taking over. This is going to be the only light bulb around in the near future. These guys will be like, go to the museum to go see them. But when you go and buy these guys, you can buy them with a specification known as their color temperature. And what color temperature is a measure, if they're trying to simulate white light, they're trying to simulate the white light produced by a surface at what temperature? If you want the temperature of the sun, as in sunlight, you want something between about 5,500 Kelvin to 6,500 Kelvin. This is the very high color temperature. Kelvin is a unit of temperature, very similar to Celsius, just shifted a little so that zero is the real zero, absolute zero. In any case, when you buy light bulbs in the 5,000-ish color temperature range, you're going to get this version of white, which includes a lot of blue. Blue being the high frequency part of the spectrum. To make blue light out here, you need very hot surfaces. And so sunlight contains a lot of blue relative to the red. And you can see that when you pay attention. You're like, oh yeah, that's pretty blue compared to that. If that's too tough to have around the house, it's a pretty harsh light. It's often described as cold light, but that's a misnomer, really. It's nothing about it cold. It is only cold because it makes you feel that way. It's really hot. It is a high temperature, high color. If you want a sort of a warmer light, again, warmer is a misnomer too, but it makes you feel warmer. Candlelight, romance, all that. Then you want a lower color temperature. You want around 2,700 to 3,000 Kelvin. So when you go shopping for light bulbs of any sort these days, if you went and bought incandescent light bulbs, you had no choice. But now that you don't, now that you buy these high-tech bulbs, pay attention to the color temperature, because you probably do care. If nothing else, you don't want your apartment lit half with one and half with the other. It looks weird. It's you're going back and forth between this and this. It's crazy. So pick one and stick with it.